Anybody? Working feverishly. Calculators are coming out now. Answers are about to happen. I gotta say, I think I need to talk to Apple. I feel like I'm selling a few of these Apple pencils. Because there's more and more just floating around. I think I need a kickback or something. Don't you think? Like you should get a discount and then they should pay me.
It's always interesting to me how many educators use Apple products.
Yeah. Yeah, me either. I don't know. I've used it all. Anybody have a time for me yet? 4.52? Yeah, okay. I like that. So T is 4.52. That's how long the coyote is in the air. But we're trying to find the horizontal distance. In other words, we're looking for XF. But now that I have time, that's something I can find. Okay, so we could use the, let's see, the exact same equation in the X direction. And we have everything we need there. X initial is 0. V initial X is the 51.58. The time we just found. Acceleration is 19. You can plug all that in and find X final to be 427 meters. Wow, that's quite a long time in the air. 427 meters. It was quite a flight. All the while dreading the end of that flight. I don't know, roller skates? Maybe the coyote's got skills, you know, and just lands and sticks the landing and just keeps on going. Who knows? Let's see. So that solves part B here. Any questions so far before I change to the next slide and answer the last part of this problem? Anybody? Anything? Oh, I'm going to move it over. Here we go. So for whatever reason, I copied over more than I needed to here. Like this is all the same thing as before. Part C is determine the components of the coyote's impact velocity. You gotta love the way they phrased it. Impact velocity. That's what he wants to hear. In other words, I want to find V final X and V final Y. Those are the two components. It doesn't ask me to find V final, where I have to put them back together and get the overall velocity. Just V final X and V final Y. So, turns out we can use the exact same equation again for both of these. We can find V final X with the easiest of the three equations, and we can find V final Y with the easiest of the three equations. Same equation, just one in the X direction, one in the Y direction. So this is 51.58 plus 19 times 4.52, which gives me 137.46 meters per second in the X direction. Wow, that's fast. 137 meters. How far away would that take you? Probably easily out the other end of this building, roughly, in 1 second. So moving quickly sideways. Vertically, we started here with 0, and now minus 9.8 times 4.52 seconds. The final velocity in the Y direction is minus 44.3 meters per second. So we're moving faster sideways than we are down at this point, which gives me a little hope for the roller skates. At least it's not a situation where we're moving more down than sideways. And it's not so good. We've got a lot of sideways velocity, so I don't know, maybe like throw the arms out and try to like keep your balance and all of a sudden just like land on the roller skates and keep moving at 137.46 meters per second sideways. Yeah. So, questions. We're done with this problem. As soon as you'll let me, I will move forward so we can get through as many of these as possible. Yes?
It's like wheel people,
Yep. Save you the stress of having to make sure you get every little note down. Yes.
Do you want us to write in X and Y components?
You could combine these and write it like this. -44.3 y hat. Same exact thing. So you could combine those. It didn't specify it had to be written that way. Okay. Next problem. The next problem takes us back to vector addition. Vector addition. So we've got a plane that flies from base camp to Lake A, and then from Lake A to Lake B, and then from Lake B back to base camp. So 3 vectors that sort of make the loop. So if we look through these, it looks kind of something like this. Maybe we have a base camp, and then we go sort of off this direction. They called that vector A, and they said that this was 20 degrees. 20 degrees north of east. So east to the north side of that, and we're 300 kilometers away. That takes me to Lake A. And then Lake B is 240 kilometers, 30 degrees west of north. So not north, but 30 degrees over to the west side of that. So instead of going straight up, we're going to go kind of, I don't know, sort of over this way somewhere. And that gets us to B. Yes, these angles are not correct, but you get the idea. And that's 30 degrees. This is vector B, and it is 240. And then it says vector C just goes from B all the way back home. So our last vector looks like that. That is vector C. Currently, we don't know anything about that. Okay? So we go to A to B, and then back home. Now, for whatever reason, I didn't put the question up there. So I should tell you, there are 2 parts to this question. First of all, what is the relationship between A, B, and C? What is the relationship between A, B, and C? If we take a look at the diagram, we can see that by going along those 3 vectors, we end up where we started. If I end up at the exact same place I start, how much displacement is that? That is 0. Okay? Notice also that I've added the 3 vectors head to tail, right? A plus B plus C brings me back to where I started. In other words, the relationship is adding these 3 gives me nothing. No displacement at all. You have not been displaced from where you started. You went on a journey, you went all these other places, you covered some distance, but you came back to where you started. No displacement. So, here's the thing. The second part of this problem is find the distance and direction from Lake B to what they call it, base camp, back home. Find the distance and direction from B back to base camp. In other words, we're trying to find that vector C, whatever that may happen to be. Yeah.
Wait, is this a right triangle?
It's not a right triangle, sadly. Would be nice if it was, but alas, it's not.
So what I was thinking, like, you know where you draw through the dotted line, like a 20-degree mark?
Mm-hmm.
I guess, like, make a right triangle out of that so you could find out the length between BC and, what's that, A?
This one?
Yeah.
Yeah, so we are going to make a triangle down there. I like that.
And then do the same thing for the top one also.
I like that.
Although,
And then do what with that?
from there, I don't know how we would get to the last letter.
Okay. Let's step through that. So we are going to do what you said. Give me a second to get there.
Oh,
And let me describe one thing first.
Okay.
Sound good?
I wasn't trying to.
Oh, no, you're fine. You're fine. No, I like that. So we are going to break these into components. Let me let's go ahead and draw those in. So we're going to take vector A and express it as so much to the east and so much to the north, which is the exact same thing. We're going to take vector B and say you have to go so much to the north and so much to the west. And that leaves us with like being up there at the top, right? It's like if I go so much to the east and then so much north and then so much back west, I've gone from base camp up to B. Let's do that for starters, okay? So let me just go ahead and add A plus B. All right? And we can do that by breaking these into components. So this side will be 300 times the cosine of 20, and this side will be 300 times the sine of 20. Look back at Tuesday's class if you're still a little worried about like, oh, how do you decide on which trig function to use? And then for that top triangle, this side will be 240 cosine 30. And this one will be 240 sine 30. We'll have to figure out what all those are in a second. Okay? So if I want to add A plus B, we do that like this. We add vectors. So we could express these in terms of so much in the x direction and so much in the y direction. And then we'll add up those columns. Okay? So for vector A, this is my x component. What is 300 cosine 20? Help. Anybody?
102.606.
102?
0.606.
6 will be good enough. There we go. So 102.6 in the x direction, and then 300 sine 20 in the y direction, which is...
No, 300 sine 20 is 102.
Oh no! Let's see.
And then 300 cosine 20 is 281.
281.9. Okay. So that makes sense. We're going farther in the x direction than we are in the y direction, which seems to agree with the way that I drew that angle. Okay. Let's do the same thing for that next vector. So 240 sine 30.
101. It's kind of shocking. It's on the dot.
It's just 101?
No, 120 on the dot for 240 times sine 30.
Okay. 120. Beautiful. I like it. Okay. Notice I put a negative sign in front of that simply because it's pointing back to the left. Okay. And then for the other one, 240 cosine 30.
207.85.
207. Yeah. Okay. So we calculated those 4 components and plugged them into the appropriate places. And then we're just going to add these columns. So 280.9 minus 120 looks a whole lot like 161.9. And then 102.6 plus 207.85 is somewhere around 310.45. A plus B. Think about what we just did. Take a look back at the diagram. Okay, question?
We could make a rectangle out of like, the excess, like, or, you know, where the green lines are.
Uh-huh.
We could start subtracting lengths to make another red triangle on the other side.
Subtracting lengths?
Yeah, like, so 300 minus cosine, 300 cosine 20 minus 240 sine 30 would be the distance from...
I see what you're saying. So, in other words, let's find something here. So this vector minus that vector leaves whatever this distance is.
Right.
And if you look over here, ooh, we did it. So what you're thinking intuitively that you want to do is what we just calculated, which means this 160 something, if we were to draw that in here, that's like this distance. And I hesitate to draw more numbers in there, but you get the idea. That's 161.9. Whee! I'm not sure if that's any better. Okay? And then taking these vertical things, like this much up, and then that other thing up, that is this plus this. In other words, that is this line. Okay, so this 310.45, is that. Okay, take a look at what we did with the green lines and how they give us those purple lines. Okay, we added some things together and that's what we're left with. Notice we essentially found how to get from base camp up to point B, which is what we did by following these other two vectors. Just another way of getting there. Okay? So in other words, if we were to add these things together, I'm going to get this vector. A vector that points straight from base camp to point B, which is almost what I'm looking for. So notice, it asked me for find the distance and direction from B to base camp. Well, that's pretty close. The distance, no matter which way I go, if I go from base camp to B or B to base camp, the distance is the same, okay? So if I can find the hypotenuse of this triangle, I've got the distance. Who cares which way the vector points? So we could say that C, at least the magnitude, is going to be the same as the magnitude of minus C, whether it's pointing up that way or back the other direction. The magnitude is the same, and it is equal to the square root of 161.9 squared plus 310.45 squared by Mr. Pythag himself. Okay? Finding the hypotenuse of that triangle. What's that number? I've got it here somewhere. What'd you get again? 472? Take another look. Take one more look. Square them, add them, take a square root. Yes.
Is it to me? Yes, to me. I got 350.12 minus. Should we round it up to 13?
Yeah, 350.1. It should be good enough. Good. 300, not kilograms, kilometers. There we go. So we're using these two as the legs of a right triangle, finding the hypotenuse, which gives us about 350 kilometers. Those other two paths were just the long way around. If I wanted to go straight there, it's 350 kilometers away. Okay? Pausing for thoughts and questions before we do the last little part of this. Yes.
So that's how you find the distance, right?
That's how we found the distance. Yeah, so distance, boom, right there. Okay. Oh, sorry, go ahead.
And then what did we say the direction was?
We'll get there.
Okay.
Next step. Yes.
Maybe I'm confused. Is there any reason why we couldn't use the law of cosine?
The law of cosines. You could use the law of cosines, but we don't talk about it in this class. So, yeah.
Isn't it more complicated,
Is what more complicated?
the law of cosine?
It's kind of a convoluted equation, but I wouldn't say it's complicated.
Wait, can we do that in 2226 or 227?
I don't know. Maybe somebody knows. I'm not sure. Let's talk direction. Let's talk direction. So, what did we just find? We added A and B. Remember this original relationship up here? A plus B equals C. Well, if I rearrange that, A plus B equals what? Negative C. A plus B equals negative C. Oh, well, take back a look at our diagram, right? Remember, negatives just flip the direction. We said C goes from B down to base camp. Negative C starts at base camp and goes to B. Oh, well, that's what I drew. I just found negative C. Well, that's a little weird. The thing is, if I want the direction from up there down to here, I actually want the vector going the other way. How in the world do I do that? The magnitude is the same. I just want the direction to be like 180 degrees the opposite direction.
So you're just flipping the positive or negative.
Yeah, that's it, right? Think about this a little bit. Let's go look at this. If the vector is pointing from here up to there, I went positive in the x direction and positive in the y direction. If I want to go the other way, well, what if we just go negative y direction, negative x direction? Just traverse the two vectors exactly backwards from what you did. Okay, it's the same triangle, just a matter of which direction that you go. So technically speaking, if we want to find that top angle, oh, let's see, which one do we want to find? Do they ask us which way to do that exactly? No, not really. So let's see, I want to find this angle, okay? I'm not concerned about the bottom one. That would tell me something about how to get from base camp to B. I want to know which direction I need to go to get from B to base camp, okay? So to do that, we could use the inverse tangent, and the opposite side is that x component at the bottom. So it's 161, and the adjacent side is 310.45, which means theta is some number I don't have. Anybody got it? I feel a cool breeze at the moment. Please keep coming. What we're doing here is using the inverse tangent, the opposite side from our angle over the adjacent side.
27.
I have 0.48
27? 0.48?
radians.
Ah, you need to convert that to degrees. 27.5 degrees,
Yeah.
maybe? Yeah, switch your calculator over. 27.5?
How do
Okay.
you know it was 27.5?
Well, I have a number here that I thought might be it.
Oh.
And then she just told me the answer. And then you said yes. So it all kind of came together at the same time. 27.5 degrees. And that is west of south. So not south, but over to the west a little bit. So if I'm standing at B, I'm like, ooh, I don't want to go south. I want to go this direction. And I want to go 350 meters or kilometers in that direction. 350 kilometers. I don't want to go 350 kilometers. It's a long way. In that direction, I'll get back home. Okay? Yes.
So theta would be from B to base camp,
Mm-hmm.
not base camp, not that angle.
Right. If we found this one, would be finding something about the direction to go from basement to B.
How is it west of south again?
West of south just means you're to the west side of the south direction. So instead of south, we're that many degrees over to the west. Okay. Yes.
So 350 kilometers is our magnitude for C,
Yes.
and then if you use that to find the unit vector, would it be the same answer?
If you use that to find the unit vector, you lost me there.
So if you convert, you know, negative C is 161.9 in the x direction and 3
Uh-huh.
145. What if you used it as a unit vector, like divided by, like 161.9 divided by the magnitude, which which gives you the, doesn't that give you the direction of the?
No direction information isn't going to come directly out of that. Need to do some angle calculation. Okay. Who else? Let's keep moving. Let's jump over to this. Let me see what's there. Hold on. Hold on. Okay, let's jump over to the force problems and come back. I want to do a couple of these. Let's see. So starting with number 9. Let's do number 9. A large box is sliding down a frictionless inclined plane of angle theta. The box has an acceleration. What is the value of the angle of incline? Q. Why is a Q there? I don't know. Something happened with symbols. That's just theta. Hint, you'll need to use inverse sine. See your instructor if you don't understand. Hi, I'm your instructor. I'm here, so that'll be helpful. And then part B, what is the box's apparent weight? We called apparent weight something else. Do you remember? One of the forces we had, we said you could also call this apparent weight. Normal force. The normal force is the same thing as the apparent weight. So we're going to be trying to find theta and the apparent weight, which is the normal force. Okay? Theta and the apparent weight. So let's go over and put in a new slide here so we have somewhere to work. There we go. There we go. So let's draw the diagram first. We have an incline at an angle theta. And it said there was a box. What was the box doing?
Sliding down.
It's sliding down or up? Which way is it going?
It's 5.6.
Okay. So let's say maybe it's there for starters. And it's going down and it has an acceleration this direction. We are told the mass is 5.6. And did they give us anything else? The acceleration is 4.3. And I think that is all. So let's start by drawing a free body diagram for the mass. So we know what the situation looks like, but I'm just going to focus on the mass itself. Remember, the rule was if it's moving in a direction, let that be one of your positive directions. So it's moving down and to the left, so I'm just going to say that down and to the left is positive x. Down and to the left is positive x, which puts a restriction on where y is going to be. It needs to be perpendicular to that, so I'm going to make it perpendicularly up. Positive x and positive y. Then we have to figure out which forces are acting on the box. Can you name one? Normal force. We hope the normal force is there. We want to find it. Normal force is perpendicular to what it's resting on. What else? Gravity. Gravity points down every time. So there's gravity. Is there anything else? It specifically said it was frictionless, so we don't have to worry about that. There are no strings or anything like that involved. It's just like, well, somebody set the box there and it starts sliding, and it accelerates at 4.3 meters per second. These are literally the only two forces that are acting on the box, trying to make it do anything. Okay? So once we have the forces, we can write out the sum of the forces in the x direction and the sum of the forces in the y direction.
What was the question asking?
It's asking us to find theta and the normal force. So, notice the normal force is pointing in the y direction. That's kind of nice. We're going to be able to work with that directly. The gravitational force, though, is not pointing in either direction, which means you have to do what is your favorite thing of all time. and break it into components. We need x and y components of the gravitational force. So let's write that in. We can draw a leg of a triangle that goes that way, and then a leg that is perpendicular to that, and points in the x direction. So one that's in the negative y direction and one that's in the x direction. You might look back in your notes and remember that the angle of incline will always live right there between the straight down direction and the negative y direction. Which means that this side will be FG adjacent, so that's cosine, and this side is the opposite, so it's FG sine. And once we have that, you can see that I have two things in the y direction, one that's pointing down and one that's pointing up, and only this one vector that points on the horizontal axis, the x direction, okay? So going back to the equations, we're going to do exactly what they say, and they say add up the forces. Specifically, add up the forces in the x direction, so this one is F times FG, F sub G, times sine theta equals MAX. And the other one has two. It's got one in the positive direction and one in the negative direction. Which leads us to those two things. Notice, we're kind of ignoring what the questions are. We don't really need to know yet. Let's just see where this takes us. Remember, the procedure is free body diagram, write out Newton's second law in the x and y direction, okay? Eventually, you're going to get somewhere and be like, okay, I've got some equations. What can I do with these things? What did it want again? But if you can do all of this, you get like a lot of the points on the problem. Half, maybe more than that, depending on how much there is to do after you write the equations, okay? This is the bulk of the physics. Like, we've done the physics at this point, okay? So that's what I'm going to be focusing on the exam. So let's see, where can we go next? We have an equation for Fg, the gravitational force. It's always the same. It is something times something. Gravitational force. You can do this. I heard, no we can't. You can do this. No we can't. What's the gravitational force? It always has the exact same equation.
9.8.
That's part of it. That's G. M times G. M times G. Always, always, always. So we can plug that in everywhere we see FG. I'm going to do that there, and then we'll go down here and do the exact same thing. Take a look at this equation under the x part of things. Well, first of all, the m's cancel out. That's kind of nice. Let's get rid of those. We didn't want them anyway. There they go. G is 9.8, and they gave us the acceleration. That means I can solve for theta, which was the first part of the question. Nice. Okay, so let's see. Sine theta is equal to ax over g. So theta is going to be the inverse sine of ax over g, which is inverse sine of 4.3 over 9.8. That gives me 26 degrees. So Newton's second law in the x direction led directly to one of the answers. You might guess the y direction is going to lead us to the other answer, okay? How much acceleration is there in the y direction? The y direction is this way. The box is moving this way. What's happening in the y direction?
Being pulled that way.
Being pulled which way?
Or the
It's not moving in the y direction.
No. So it is being pulled this way, but simultaneously being pulled this way an equal amount, which means that it's staying on the slope itself and just sort of going down the slope. These two things are equal to each other, which means that there is no acceleration. All of the acceleration is in the way we've defined x direction. None of the acceleration is in the way we define the y direction. Which means that we can solve this now for the normal force. Fn equals mg cosine theta. And we've got all of those numbers. 5.6, 9.8, cosine of 26, which we just found from above. Which gives me 49.3 newtons. You might have noticed a trend. There's some things we've been focusing on. We've done a whole lot with vector components, splitting things into components. We've done a whole lot with adding up vectors and finding resultants and displacements and things like that. We've done an awful lot with free body diagrams and writing out the two equations and see what you get. We've done an awful lot with kinematics, right? Writing out your variables in the x and y directions and seeing where things go. I just wrote the exam right there. Those are the important things.
Wait, those are the questions in the exam?
They might as well be, at least in some version of that. Kinematics, adding vectors, dealing with vector components, forces and free body diagrams. Over these first 4 chapters, those that are 5 chapters, those are the important topics. Those are the big topics. If I were writing an exam, it would include those things. That's all I'm saying. It really would.
Can you see that?
I don't know if I can. Like, do we have to-
And then the last one,
To the
vectors and vector components. What's the last one? You said one more.
adding vectors, dealing with vector components, those kind of go together. Kinematic stuff, forces and free body diagrams. I think that's all I said. The exam is a work in progress. These are just some of my thoughts. Okay? So let's do another one of these real quick, and then we'll go back to the other slides. Let's see. Let's do number 11, just because it's a little ridiculous. And no, I did not write these, even if you think I did. I promise I did not write these. So this problem involves someone known as Turner Fernswapper, who is known by his friends as Twinkie. I think whoever wrote this, and I know the guy who wrote this, probably had a couple of extra drinks, and it was like 1 in the morning, and he's like, I gotta finish writing this thing. And then out comes Turner Fernswapper for some reason. So he makes a career of being different from everyone else, and the recent weather has given him no excuse to do otherwise. So while the other kids are jumping on their sleds, wow, this does not translate to California at all. You're like, sleds? What are sleds? They're things you play in the snow with and slide and stuff, all right? And other people are speeding down the hill. Twinkie decides to place his sled at the bottom of the hill and then run and jump on and see how far up the hill he can slide. To me, this sounds like one of the kids that tries to push things with a rope. You know, same kind of idea, a little bit different. Things are a little strange. So Twinkie finds he can slide up the hill 2.5 meters. It's all, for all practical purposes, frictionless. They give us the mass and the angle. Okay? So I'm not even going to read the questions. Don't read the questions. We don't care about the questions. Let's see what happens. And page below, there's a page. Beautiful. So we've got something that looks like this again. Incline. This time they told us the angle. They said it was 22 degrees. Twinkie and his sled. Sounds like a song or something. Twinkie and his sled. Starts with some velocity, like runs, jumps on, and then some velocity this way. And then you can imagine like goes slower and slower and slower, and eventually up here is going to stop. And it told us that this distance was 2.5 meters. Here's the thing. First of all, you know that this is in a document that's about forces and free body diagrams, so you know that's involved. But second of all, I've got a distance that's being traveled there, and I've got something about a velocity. That should make you start thinking kinematics. And the fact of the matter is they're both kind of tied in together here. So we've got one problem that's covering two different chapters at the same time. I like that. No, that one's not giving me ideas, but you know, there we go. So we're going to use forces and kinematics in this problem. So let's start by drawing a free body diagram for Twinkie and his sled. And since it's moving up along the incline, this time I'm going to call that the positive x direction. And then perpendicular to that, we'll have our positive y direction. What forces are acting on the sled? Name one. Go.
This is just like the previous
Oh,
problem.
it's an awful lot like it. Yes. There's gravity. There's a normal force, right? So we're going to work this a little bit faster. We got a normal force this way. We've got a gravitational force that points that way. And we know we can break that gravitational force up into components. So this will be theta, which is our 22 degrees. So this is Fg sine theta. Notice it points in the negative x direction this time. And this is Fg cosine theta. Which means we can write out the sum of forces in the x and y direction. And we should be pretty good at this time. There is acceleration in the x direction, right? He's slowing down until he stops. That means his velocity is changing. So we're going to keep that around. And it turns out that we have negative Fg sine theta that is causing that. So let's go ahead and finish working this part through. So that's minus mg sine theta equals max. The m's cancel. This time I know g and theta, so I can find a. So ax is going to be minus 9.8 sine 22, which is minus what? Some number I have here somewhere. I don't know, 3.7. Are you okay with that negative sign? Often when you see a negative, you should step back a second and be like, all right, what's happening here? Does that make any sense at all? Remember, the velocity is up that way. A negative acceleration means there's an influence the opposite direction, which will result in a slowing down. So that fits exactly what's going to happen, right? You go up a slope, you're going to slow down as you go higher and higher. So we've got the acceleration. Let's see what comes of the y direction. Once again, there is no acceleration in the y direction, and I have Fn minus Fg cosine theta. Yes, this one sets up exactly the same. So that's Fn minus mg. So Fn is equal to mg cosine theta. And we have those values. I don't know what the answer is. You'll have to tell me. Some number. Anybody? Don't all jump at once. Calculate like this. Does anybody calculate like this? I don't think so. With two fingers, like on your calculator. Mass times gravity times cosine theta. Answer. Nobody wants to help. I'm so sad. I'll just leave. Bye. One of these days I'm going to leave that way. Just crawl right out the window. You're not going to care. Actually, I'm going to have trouble fitting thanks to these things. Oh, that one's broken. I can go out that one. This one I can. Does anybody have the value for the normal force? No?
Cosine of what value?
22.
Degrees, right? Not radians.
In degrees.
Yes. 0.927.
Sounds awful small.
That's just cosine of 22.
Oh, gotcha. times 9.8 times whatever that mass was. I don't remember. What's that? We were, yeah. It is 65. So 65, 9.8, cosine 22. Hmm? 6, something I thought I heard. I don't think it's that big. I like how people are calculating out of desperation now. Just like, I want to move on. I'll calculate if I have to. It's not right? No one trusts their answer, huh?
I don't think 590 is the right answer.
That seems right. Yeah. 590 newtons. Yeah. That's the support force from the surface. Ah, there we go.
I was thinking of going down
No,
onto the side.
we're not there yet. No.
I was like, you can't put 590 newtons of force onto a sled and have it sail.
Have we answered the questions? Part A, draw a free body diagram. We did that. Part B, find the x component of acceleration. We did that. Part C, what is the initial speed? We didn't find that yet. Okay, so let's go back over to this. Notice, we could say that the starting point is here at the base of the hill and the final point is up at the top. There's 2.5 meters between the two. We could say that this is x equals 0, and why not just let up be the positive direction just like we did for the free body diagram. If we do that, we have our 6 variables, x initial, x final, that's 0 and 2.5. V initial is what we're looking for. V final is what? 0, yeah, sled stops. Acceleration in the x direction is negative 3.7, as we found below, and the time is unknown, which means we have enough information there to find the initial velocity. To do that, which equation do you want to use? I want to use this one. You're like, yeah, that was the one I wanted to use. That's exactly what I was thinking. You read my mind. And it's halfway solved for you. Just move a few things around and see what you get. So the final velocity is 0. The initial position was 0. So negative 2ax x final equals velocity initial x squared. And then we will take the square root. If you plug all that in, again, don't forget you get a plus and minus when you take a square root. Look for the one that makes sense. He's moving in the positive direction, so positive is going to be the answer you want. And you should get positive 4.3 meters per second. Which means you can run pretty fast, it turns out. Wow. He can really move. Does anybody have any questions before we go back to the other and do some more problems? We've got 14 minutes of review remaining. Question?
So the equation, is that a 2 next to the acceleration?
It is.
Okay.
Yeah, it's the fourth kinematic equation, number 4 in our list. Anyone else out there? I'm about to tap back over to the other slides. Okay, there we go. So let's see. Taking a look at these 3 problems, they're all so good. I can't decide. You want to vote? Does anybody want to pick one? So we've got this thing with the graph. We've got this thing with some circular motion stuff, and then we've got this thing with an elevator and a bolt.
Whatever.
Wow, I don't know. Who says elevator and bolt? Who says circular thing? Who says the graph at the end? Okay, so we're going to start with the circular thing and see where that gets us. And if there's any more time, we'll do one of the other ones. And if there's not, I'll fill in all the answers for you and post it online. All right? So we have an automobile whose speed is increasing at this particular rate. Notice a couple of things. Meters per second squared. That's an acceleration. Increasing speed, acceleration. Okay? And we're on a circular road of radius 30 meters. So let's start with a circle. Whee, there we go. And let's say that it has a radius of 30 meters. So R equals 30. And let's say that the car is right here. And it's going to have a velocity that's tangent to that circle. So there's my velocity. I think there's something over here somewhere. Because a few minutes ago, I felt something crawling on my neck. And that'll freak you out. So I was like, spider! And then I didn't see anything. So it was probably just a bee or a fly or something. But there's something over here somewhere. If you want to see me freak out, watch me pull a spider off my neck. And then I'll just jump up. It'll be fine. Don't worry about it. So there could be a spider over here somewhere. So keep your eyes open. And if you see it, please, take it home as a pet or something. I don't know. So let's see. When the instantaneous speed of the automobile is 4 meters per second, in other words, when the velocity here is 4 meters per second, find the tangential acceleration component. What? Tangential. So tangent. Tangential, tangent, something that's tangent to the circle. In other words, it's wanting us to find the value of the acceleration that points in the direction of the velocity. That would be a tan. It's tangent to the circle. Remember, we talked about accelerations a little bit. This is the component of acceleration that speeds up or slows down the object. So when it's moving in a circle, this is the part of the acceleration that makes it go faster or slower. If it's pointing in the same direction you're moving, it's going to make you go faster. If it's pointing opposite to the direction you're moving, it'll make you go slower. Notice it said the speed is increasing at a rate of 0.7 meters per second squared. It's telling us how much it's accelerating. Specifically, how much it's accelerating tangent to the circle. So, very deceptively, they gave us the answer to part A. Part A tan, is 0.7. You got to really hate that when the answer is just right there. Then you go off and you do like pages of work. You flip through the book. You're trying to find answers, only to discover that they tried to make it easy. Sometimes making it easy makes it hard. Feels like a theory of some type. I don't know. So the tangential acceleration, the tangential component is the one that makes it go faster or slower. There's another component to the acceleration, one that is perpendicular to the velocity. Remember, it's called AC, or centripetal acceleration. This is the part that only changes the direction of the velocity. So it's kind of like I'm trying to just go straight, but people are pulling me two different directions. Something is pulling me forward, and something is pulling me sideways. The thing that's pulling me forward, makes me go faster. The thing that's pulling me sideways turns me, okay? Those two things operating together make me go in a circle faster and faster and faster and faster, okay? Yeah, okay. Do you want to do the experiment? Do y'all want to drag me around the front of the classroom? A few of you are like, yeah, I'll drag you around the front of the classroom. I'll drag you right out in the hall and make you eat your iPad because I'm sick of physics. I hope nobody's thinking about that. That's just mean and terrible. Wow, please don't be that way. So, B. B says, what is the centripetal acceleration component? We have an equation for that. AC is V squared over R. So V is 4 and R is 30. Wow, that was fast. I need the other notes to know what the answer is, though. 0.533. And please don't forget that your numbers may be different than mine. Don't let that freak you out. It's the ones in red that are different for every given iteration of the problem. And then finally, C takes us back to what we've done several times today, which may give you some hint as to whether or not it's important. So these are perpendicular, right? A tan and AC. And part C is asking me about the total acceleration. That means these are components, put them together, and find the hypotenuse. So if we were to draw this out head to tail, we would say that AC points this way, and then perpendicular to that is A tan, which means that the hypotenuse points kind of like that. And that is a total, which we can find using whose theorem? Pythag. Mr. Pythag. Dr. Pythag. I don't know. Who knows? So let's see. A total is the square root of A tan squared plus AC squared. And those are the two answers we have from above. Why am I back over here again? I'm going to have that spider on me again in a second. It's freaking me out. So let's see, I've got 0.88 meters per second squared for that. And it asks for the direction as well, so the direction takes us back to finding an angle. So an inverse tangent, once again. How many times have we had Pythag and inverse tangent recently? It seems like it's happening all the time. So Pythag and inverse tangent. Pythag and inverse tangent. Got that? Next Tuesday. Pythag and inverse tangent. We seem to have to do it a lot. So this angle theta, I'm not sure what that is. Maybe something like 52.7 based on other things that I have here. That would be from the tangent. So tan minus 1. 0.7 over 0.533. Just totally out of range. Wee. Go bigger. I know it's too big now. Take it away. I'm making you dizzy. All right. We've got time for one more, but there's only one option. The one takes a long time, the other one takes a short amount of time, which means I can do this one in the time that's left. I will give you the solution to the other one, and I'll try to put in like extra handwritten notes to explain what I'm doing so that you can review it for yourself. So here we have a particle that starts from rest and accelerates according to the graph below. So this is acceleration versus time. They want us first of all to find out how fast it's moving at 10 seconds. How fast it's moving at 10 seconds. So I know that the velocity at the beginning, or let's write this as velocity at 0 seconds. We'll do that, is 0. We're trying to find the velocity at 10 seconds. Well, I know the acceleration, and I know the time. That means I could say V10 is equal to V0 plus acceleration times time. Notice that's a kinematic equation. And this is 2, looking at the graph. And the time is 10. And we don't need a calculator for that, I hope. 2 times 10 is 20. So at 10 seconds, we're moving 20 meters per second. We sped all the way from 0 to 20 meters per second. How fast am I moving at 15 seconds? $20 meters per second. There's no acceleration between 10 and 15. So I'm still moving 20 meters per second. This next part wants me to find how fast I'm moving at 20. Notice now I have a negative acceleration, which is going to take my velocity down some amount. So to do that, let's say V20 is equal to V15 plus acceleration times time. So I'm going to use a new interval there, where V20 is the final velocity. And we could say that this was 20 plus -3 times 5 seconds. -3 is the acceleration here, and that lasts for 5 seconds. So 20 minus 15 leaves me with 5 meters per second. Okay? So I go from 0 up to 20 meters per second, stay there a little bit, and then decelerate back down to 5. Right? If we want to answer this last question, and there's just enough time to do it and still let you out a minute or two early, how far did we travel for this whole thing? Okay, so to do that, we're going to follow the same sort of procedure. We're going to say, first of all, between 0 and 10 seconds, we can use our first kinematic equation. And this is 0, and that is 0, so I have 1/2 times 2 times 10 squared, which looks a whole lot like 100 meters. For the first 10 seconds, I traveled 100 meters. For the next 5 seconds, so from 10 to 15 seconds, we're moving at a constant velocity. I'm moving 20 meters per second. We already determined that, and I do that for 5 seconds. So that's just 20 meters per second times 5 seconds, which is another 100 meters. And then finally, from 15 to 20 seconds, now I'm slowing down. So what we want to use here is this equation again. And let's just go ahead and say that we're starting at 0 because I just want to see how much I move during that last bit so I can add it to the others. And we start by moving at 20 meters per second. And then our acceleration is -3 for those last 5 seconds. So starting at 20 meters per second, acceleration is -3, 5 seconds is the time. And for that part, you get 62.5 meters. So if I add all those up, 262.5 meters for the full 20 seconds. Okay? And we are out of time. I will post this in the near future, hopefully sometime this afternoon, depending on what I get bogged down with. If you have questions over the weekend, don't hesitate to email, take a picture of what you're working on. Let me help if I can in that way. Otherwise, I'll see you here on Tuesday. Good luck as you study. Bye. Bye. I'll miss you all. Okay, you don't exist. What's that?
Just doing the wording.
Concepts like the multiple choice we had in class,
Yeah.
and other problems that are sort of like you look at it, do a quick analysis, and maybe give an answer. Stuff like this is good for multiple choice, analyzing the graph. 75 minutes of fun or something. 2 to 3.